Hi everyone. We'll start within a few minutes. Hi, so I guess everyone can hear me. So, start with today's session. So welcome to today's lecture about the course titled as Semiconductor Devices and Circuits. So my name is Shomnath Bhattacharya. I am taking the problem solving session week 3. So we have already completed half of this course, and so, you all know already about me, but let's have a brief introduction. So, I am pursuing my PhD in the Department of Electrical Engineering at IIT Jodhpur. I am working on thin film transistors, organic thin film transistors, specifically towards neuromorphic computing applications. And our general class schedule is from 7 to 9 on every Sunday. So this is the basic course structure of our this course. So as we have already completed half of this course, so let's start with a brief introduction of what we have already learned and what we'll learn afterwards. So at first we have started with this the excursion of quantum mechanics, in where we have learned about the Schrodinger equation and how to solve them, and in various cases where we have to solve them and how do we have to solve them and those things. Then after that, in the next class or next session, we have learned about how this original equation can be used for different types of solids, and different types of solids and like amorphous and crystals and those things. And afterwards, we have learned about the Fermi function, and different types of doping in semiconductors, what are semiconductors and those things, and density of states, where the electron can be found in a specific material or something. And afterwards, we have learned about the recombination and generation, that is electron hole recombination and electron hole generation through a photon. And after that, we have learned the charge transport, how the transport phenomena is going on based on the movement of these electrons through a solid. And afterwards, we have learned about the continuity equation. Then what we have done, we have connected this impure semiconductors, that is the n type and the p type semiconductors together, and we have got different types of junctions. So we also have metal with semiconductor junctions and also semiconductor with different types of semiconductor junctions. So metal semiconductor junctions, we have learned so many things about them. After that, we have learned about how to dope a semiconductor different with different types of impurity in a single case. So there was p-n type junctions, there were several p-n-p and those different types of junctions, where we have learned the band bending phenomena, and how the band is getting bent, why we have to align the Fermi levels of each of the sides, why we have to align the Fermi level of p and n, and based on that, there is the band bending phenomena going on the EC and EV, that is the conduction band and the valence band. Also the vacuum level, there is a bending going on, and how this bending is characterized and why this bending is necessary to learn and those things. Afterwards, we have the final thing we have learned about, there are different types of diodes that can be made based on this kind of a semiconductor junctions, and why these diodes are important and why we need to learn these kind of diode structures and those things. Finally, we need to learn about transistors. So what are transistors? Transistors are different types of switches. um, we can say a kind of a digital switches, which can be remotely turned on and off based on electrical inputs to them. And so there are several kinds of transistors, and we have to learn the transistor because transistor is the basic building block of any kind of a circuit. So everyday electronics, let's say from fan, light, and everything has a transistor in it. And we for creating a basic circuit and everything, we need a transistor. So there are several kinds of transistor. We'll learn more about them afterwards. But so we'll start with the bipolar junction transistor, that is the junction transistors, and afterwards we'll learn about the MOS transistors and mesh transistor and those things, and how to utilize them in different kind of a circuits. That will be our kind of a final aim. And afterwards, the more advanced one, that will be like the thin film transistor that I'm currently working on as a PhD student. So like we'll move towards that. So this was a basic recap of what we have already like learned and what we're going to learn about in the next few lectures. So today's class will be focused on bipolar junction transistors. So in this, I guess there were only three lecture videos in the this week. So based on that, the basic things what we have learned is what are transistors, and how these transistors are made, and how many kinds of transistors are there. What are the difference between them? We'll learn about them later. But here we are learning about the junction transistors. That is, as we have already learned about different types of junction, that is the PN junction, NP junction, and those things. So what if we can assemble these kind of a junctions together? What will happen? Can we make a transistor out of it and those things? Then these transistors can operate in different operation modes. So we'll learn about the operation modes as well. So I'll not go into like the derivations and those things, the basic details. So I'll just omit them, but you have to learn them as well. So there are several operation modes in which a transistor, specific transistor, can work, and we can utilize it for different kind of applications as well. And so to solve to get this solutions of different what do we say, like different terminal currents and those things, whatever will derive in the operation modes. Based on that, we have assumed several ideal cases where we are assuming that these are the ideal cases and there won't be any changes. So based on that, there will be some exemptions which can be termed as the non-idealities. So we'll learn about that as well. So let's start with today's session. So the first concept we have learned this week was transistors. So as I have already told that transistors are nothing but digital switches, and they are electronically controlled. So they are electronically controlled digital switches, and there can be manual switches that can be turned on and off based on like mechanical forces and those things. So transistors can be termed as the digital switches. So there are several kind of transistors. Uh, The primary one is the bipolar junction transistor, which will be the main focus of today's session. Bipolar junction transistor. Second most important one is the MOSFET. So this one is the BJT, then metal oxide semiconductor transistor. So the from the name we can suggest that there is a metal layer, there is an oxide layer, and there is a semiconducting layer. So there are three kind of a layers in this case. So these are called as the MOSFETs. Then there is something called MESFET. So I'll maybe write it like this. So there is something called MESFET. There is something called the TFT. So this is the thin film transistor. So these are based on thin films and those things. So there are several other kinds of transistors as well, but these are the conventional basic ones. And like we'll also learn about this. So like in MOSFET, there are two types of different transistors. Those are like the depletion ones, the depletion MOSFET transistors, and also the enhancement MOSFETs as well. So these are different kind of a transistors, and one of the most simpler and one of the easier to understand at first is the BJTs, that is the bipolar junction transistors. As we have already learned about the junctions and those things, so it will be easier to understand this. So our main focus for this class will be bipolar junction transistors. So let's move on to this. So first, what is bipolar junction transistor, right? So let me write it as BJT. So what is an bipolar junction transistor? So let's say, like, let us have a junction like this. Okay, so we have a junction. It can be any kind of a junction. So let's assume it is a PN junction, a basic PN junction, right? So the basic let's write it like this, I guess. So this is a basic PN junction, and the first half is doped with P type. So the first half is a P type impure semiconductor, and the second half is a N type impure semiconductor, and both of these are moderately doped. Now, what will happen if we just add another part like this? So we are adding another part of a semiconductor, and in this case, what we are doing is we are heavily doping this part, so it can be a N plus. So heavily doped part is added with this, so it like it can look like this. So a PN junction is nothing but this, right? So in this case we are having a structure like this. So we are just connecting two diodes together. It's not exactly the same because the P type should be much narrower than a normal junction. So in PN junction, the both side. So if this was, let's say, A and this was B, so A and B can be comparable. But in this case, if let's say you are having this as an different part as, let's say, Y, so Y and B can be comparable, but A has to be much smaller than Y and B both. So in this case what happens is that so we can't consider it as like this. So let's assume it like first like this. So let's draw a semiconductor slab. So what we are doing in this case is that we are doping this part of the semiconductor with N plus impurities. That is, it is heavily doped part. So what we can do is that we can make it more narrower as, and we are doping this part as N. Uh, this one would be a straight line anyways. So for the sake of drawing, so this should be like this now. If oh sorry, and this is P type dope, and if this is the with, and so for nomenclature purposes what we are naming it is the N plus side, that is the heavily doped side, we have to name it the emitter, because it's how do we say, so N plus type, it's a emitter side because it is emitting the extra number of N atoms, so that is the, it is emitting the electrons from its side. So we are calling it as the emitter. Okay, so it has much more numbers of electrons than the other parts, and other parts. So can we delete this? Yes. Okay, now this part is the base because it's contradicting with the much more numbers of electron in this case. So we are calling it as the base, and this is called as the collector. Why it is the collector? Because these electrons are traveling from the n plus side, like in between it's traveling through the p side and it is going towards the n side. So that's why we are collecting it the collector side. So electrons are emitted from the emitter, it's going through the base and it's getting collected at the collector side. So that's why the basic nomenclature comes. So let's say if the p type part, that is the base part, has a base width of wb. So in this case, to make it as an npn, so the structure is called npn. Okay, so to make it as an npn structure, so to make it as an transitive structure or an npn transistor, the base width, that is the wb, needs to be very narrow. So this is a basic condition. Because of that, it can't be made with like two different diodes. So we can't connect two diodes side by side and call it as an transistor. That is the NPN transistor. We can't call it because the WB needs to be very narrow. So that's why this is an NPN structure. We can draw it like this. Let's draw it like, just a second. So this is the basic structure how we draw this. Let me just see. Yes. So this is kind of a structure. You can like say it. I'm drawing it like in a portrait mode. So this part is this part is the collector part. This part is the emitter part, and this part is the base part. So let's say we are having a current IC from the collector part, and we are having and current from the base part, that is the IB. And if we are saying we are having a current of IE from here, so this is a basic NPN transistor. And so also we like we are applying a voltage VC here, that is the collector voltage, and this is applied VP and this is VE. So the total current, that is IE, should be the summation of IC and IB. So emitter is like, let's say emitter is having a current, so the total current in the emitter, found in the emitter, is nothing but the total current in the base region and the collector region. Why is it? So the emitter is emitting the electron from its side and it's giving to the collector, but in between there is a bit of separation going on. That is, a bit of separation is going on in the base region, so there will be some electric current generated in the base region as well, that is a very smaller one, and a huge amount of current that is generated in the collector region based on this electron transfer. So the total current in the emitter region should be equals to the collector current and the base current. Now similarly we can also have like a PNP structure, whereas like in this case, so this one would be the P plus, that is the heavily doped P side. This is the N type, and this one should also be have a like a very narrow width. And so this is a PNP transistor, and this case as well. So this is the emitter, this is the base, and this is the collector. So now in this case, what we are assuming that it is a transport through a whole transport, but in that case, then we know that like the direction of an electric current is just opposite to the the electron movement. But in case of hole movement, let's say we are assuming a movement of holes, the electron will all electric current will also flow in that direction as well. So here in this case, the electric current flow would be in this direction as well. So based on this, if we are just a second, let me draw it like this first. Sorry. So this is the base terminal, and so VB is applied here, a VC is applied here, and a V no, in this case it will be the emitter part and VC would be here. So based on this, a current is flowing through this. Let's say that as an IE, and current is towards this side, while current is towards this side. So based on this as well, so the current will also be the same in this case as well. So these are the different two structures of a BJT, that is the PNP and the NPN transistors, and these are very similar to an diode characteristics and the diode formation. Although the in between layer, that is the base area, is much narrower than a normal diode, so we can't make it through like connecting two diodes side by side and those kind of things. Now let's move on to the more scientific things and everything. So we need to learn about the band bending diagram of this. So that's why like a good what do I say, like a good schematic is needed because of this. So I'm not drawing the schematic again, but let's say we have a P plus side here and a N side here and a P side here. Okay, and as we have already discussed, so this is a much narrower region like this. If we can move it to the middle. Okay, so this is a very narrow region, and based on this, so if we are assuming a depletion region formation here, so this part is the depletion region in the N side, and the opposite one is the depletion region in P side. Similarly, there would be a depletion region here as well. So this part of the depletion region is called as the base collector depletion region. Let me have a few minutes, just a second, right? Sorry everyone. So actually I got a call, urgent call, so I had to pick it up. So where was I? Yeah. So I was telling that this is called the base collector depletion region, and this region is called the emitter base depletion region. Okay. So this is also the depletion region, and this is also the depletion region as well. So the effective width of the base is right now this. Now, as we know that the energy levels are here kind of a, so as this is a p plus dope part, so it would, let's assume that the energy level is here, and based on this, as this is a moderately doped one, so there will be a bit lesser energy in this case. And as this is a n-type doped one, so let's say this is here, so the band bending will happen like this. And for the p-type case, it will look like this. So the basic, so we'll have a basic difference in between this as well. So this is under, also to mention that this is under equilibrium condition. So this is under equilibrium condition. Now, uh, yeah. So this, like to mention this, so this is much higher cause of heavily doping, and this part is lower because of moderately doping. So if we are just like twisting it around, so if it is an P and P plus, then the band bending diagram will just be opposite of this. So another thing to mention is that this is the emitter part, this is the base part, and this is the collector for these cases. Okay. So this is the basic band bending diagram, and based on application of different voltages and everything, it will change, and the change will be very similar to that of like in a normal diode also. Now, so we'll move on to, sorry, just a second. Yeah. So we'll move on to the different operating modes or the different operation modes. So these modes can be like characterized by several kind of a things. So based on the junctions utilized in this kind of a modes, like achieving these modes. So if we are considering which of the junctions are controlling in the controlling position of this mode, so those can be like the, sorry, emitter base mode and the collector base mode. And based on the outputs we receive from this like device structures, so those can be the active region mode. So in active region mode is also called the analog mode, because the output current keeps on increasing with a linear line. And then the second one is the saturation region, sorry, yeah, so saturation region, we can say it as the on state mode or digital on mode, because like after achieving a certain amount of current, the output current doesn't increase after that level. So it the we can achieve the maximum current for that amount of voltage, and even with applying some above voltage, we get that amount of current only. So we can say it is at the on state of the device, or the on digital in, if we are considering digital, that is a 0 and 1 case, we can say this is the one case, that is the on case. And the other one is the cutoff region. So what is a cutoff region? A cutoff region is that before achieving the active region, there will be a very small amount of current or nearly no current in the output region. Based on that, we can say it as the off state or the digital off. And the final one is the reverse region, where we are applying a reverse voltage and those kind of a things. In the reverse region, the device is working and those things. So based on these different operation modes, we can like in the videos as well, we have achieved the current voltage characteristics, and these characteristics are very similar to an a PN junction diode, and it's working. So the current voltage characteristic depends on these which of the region we are working on, and based on which of the modes we are working under. But also, like, based on this, the value of this current voltage characteristic changes, and based on this we can also get the general current equations for the devices, which are valid for each of the cases. And also from this we can derive for like different regions or different modes, what is the value of current in each terminals. So what is the value of current in like the collector, that is the IC, the base current, that is IB and IE. So we can get each of the values through here. So these are basic derivations and everything, so I'm not going to like derive those things. You can check the videos for that. So after that, the one of the most important things are the concept of different non-idealities. So the first non-ideality we need to know about is the recombination in the base region. So what is recombination in the base region? So the first like the just a second, let me check if it's going on. Yes. Yeah. So what is the recombination in the base region? So at first, when like we were constructing this NPN or a PNP transistor, so there was a basic assumption that so I guess I have omitted that. So at first, when we were considering of making a BJT, so a basic assumption was that the base width, that is WB, is very very like narrow, so it needs to be very narrow. So as I have already explained here, but why it needs to be narrow? So it needs to be narrow because like it needs to be so if base width is this, it needs to be much much smaller than the diffusion length. So what is a diffusion length? A diffusion length is the average distance traveled by a minority carrier before it can recombine. So like it can what do you say? It can be without any energy or something. Then it will recombine with another particle. So the main thing is here that the base width should be very very less because it should be less than the diffusion length. Now so the basic definition of a diffusion length is that let me write it down first, I guess. Diffusion length is the average length of a minority carrier can travel without recombining. So without recombining, diffusion length is the average length. Now the problem with this is the average length. This is not an exact length. So based on that, we are assuming that there is no recombination in the base region. But based on this factor, we can say there the basic assumption based on this was that this should be this. It was said to be zero, but it is not true because there is a very small amount of recombination in the base region. So based on this recombination going on, the total equation we have already derived and everything can have to be changed, and there have to be a corrected value of this. So this is one of the non-idealities. Then the next non-ideality is called the early effect or generation of an early voltage or early voltage. So that's it. So this is also named as the base width modulation, or in case of MOSFET there is a collector current dependency based on this. So we'll learn about that later. So if we have a BJT like this, and this is the base, right? Base region is this. So as we know that it should be much less than the ln. So ln is the diffusion length, and now the problem is that, or I will use a different color, just a second. So based on the depletion regions, so here is the depletion region, that is the base collector one, and here is the base emitter one. So these are two depletion regions, right? So right now the effective length, let's say it is as the WB, and now WB should be much lesser than ln. Now the point of this is that this value of WB is dependent on VCE. Why is it dependent on VCE? So if we are changing the value of VC, so like from this, if this is E and C, so if we are changing the value of VC based on this depletion width will either increase or decrease. Okay, so it is directly dependent on VC, and based on that as well, so if we are changing the value of VE, the value of this depletion width will either increase or decrease. So based on that, the value of WB will change. So based on VCE, so this is a function of VCE anyways. So based on the change in VC and VE, the value of WB, that is the effective base width, will change. So based on that, the output current, that is the collector current, is also dependent on VCE. So the basic concept is that based on the change in VC, the depletion width in the P and C region will change, and based on that, based on the change in VE, the depletion width between E and B regions will change, and based on that, the effective width of the base region will change, and also the final collector current, that is the output current, will also change. Now, if we draw this, the collector current. So the output looks something like this. So these are not wavy patterns. This will be a simple straight line structures and these things. So based on this, what we can do is that so this is IC. based on this, we can extrapolate these values, and all the extrapolated output currents will meet at a certain point, that is minus VA, let's say. So this voltage is looking like the basic incident point or the starting point of this output currents, and this is called the early voltage, and that's why the effect is called the early effect. And so base and this is based on the base width modulation, so the effective base width is getting changed, so this is also called the base width modulation non-ideality or the early effect, or based on this the early voltage comes in. So this is the second non-ideality. The third one is avalanche breakdown. So what is avalanche breakdown? It is a much simpler one, because if we are increasing the reverse bias, if we are increasing the reverse bias, if the reverse bias is above a certain amount of let's say there is a certain amount of value, certain amount of voltage is there, and we are crossing this limit, what will happen is that there will be a avalanche of current. So what do we mean by avalanche? Avalanche is like the avalanche flow in snowy areas or those kind of a things. That is a uncontrollable amount of current due to this high reverse bias. So there can be a concept of avalanche breakdown, and that is also not included in the current equations and those things. Now another one is the concept of punch through. So what is a punch through? Punch through. So based on let's say, so let's say the effective base width is WB, and in a case where there is a very favorable VCE, that is the collector to emitter voltage applied in a certain kind, that the value of this tends to zero. So that is that two depletion region touches. So in a case like this, let's say if we have this like a structure and the base is like this, and what happens is that we are applying a certain voltage, that the first depletion region is we can't mark it. So the first depletion region is like this, and based on this as well, the second depletion region is like this. So these two depletion regions touches each other, and based on that the effective width, that is WB, is nearly zero, let's say. And in that case, that two of the depletion region touches, so that is known as the punch through. So the voltage that is applied that is needed for this case is called as the sorry, punch through voltage. So the basic band bending diagram, I'm just drawing it roughly. So if the basic band bending diagram was kind of like this, right? It was looking kind of like this. And the after the punch through, it will look something like this. Sorry. It will look, mm, it will look something like this, because there is no, uh, what do I say? Like there is no specific width of the base region, and based on that, it will look something like this. This is band bending at punch through cases. Yeah. So this is the concept of punch through. Then the fifth one is the concept of contact resistance. So contact resistance is the basic resistance between the metal, semiconductor, or kind of a say semiconductor junction. Okay, so the basic metal semiconductor junction, there is a basic resistance. We in most of the cases like assume that there is no resistance between these two layers or these two subsequent um, what do we say, like subsequent materials and those things. So we assume that there is no resistance, but in physical cases there is obviously a resistance. So that is called as the contact resistance. So the basic reason of this is like due to surface irregularities. So, so this is due to surface irregularities, and in case of like a proper fabrication and those things, so there can be few contaminant particles as well. So based on these contaminants, there is the basic case of contact resistance. And the last one is recombination and generation in the depletion region itself. So in the depletion region, there is recombination generation going on. So this is a very straightforward thing. No need to like a explanation of this. So these were the topics we have learned through this three lectures and these things. So if anyone have any question, you can ask me, or we'll move towards problem solving. Are there any questions, or we'll move towards problem solving? So let
So,
yes.
can you once again explain about the early effect?
Oh, yes, sure. So the early effect is basically something. So let me use this. Yeah. So this is a basic structure, right? So that is the emitter, base, and collector, right? So the basic assumption was that the base width should be much lesser than the this, right? ln. So it should be much lesser than ln. Now the concept of WB is nothing but that. WB, if we are assuming that WB is the effective width of the base, right? So this effective width of base was first this when they were not connected with each other. But when it's connected, the basic width is this, right? This area is the width. The base width is this. Now, if we are applying VC, that is the collector voltage with this base. So VCB we can also say. So based on this change of VC, that is the collect change in the collector voltage, what will happen that this depletion region will change as well. So based on change in the collector voltage, the this depletion region will either increase or decrease. Similarly, based on the change of this VE, that is the emitter voltage, this depletion region, that region can either increase like this or either decrease. So we can say that WB is not a like a constant value. It doesn't have a constant value. So based on the applied voltage between VCE, so that is VC minus VE. So as it's dependent on both the terms, so we can say that it is dependent on VCE. So based on that, the change in VCE, the amount of WB changes. And if we are changing the depletion width, the current will also change. So if that so not the depletion with that the what do we say, like um if we are changing the width of the base, the output current, that is the collector current, will also change. Why it will change? So if let's say uh, the effective area of emitter is like this, like collector area is like this. So if a electron wants to move through this, it will have to pass this amount of base area, right? And if the base is this much small, if one thing has to move like this, so it will have to pass a small amount of base area in this case. So based on that, the collector current will also change. And as we know that the output characteristic is like this, right? So what happens here is that the voltage gets linearly increased, and after a certain amount of time it gets saturated. So it's going towards saturation and it will saturate after this. So if we are just extrapolating this, if we are extrapolating this line, it will meet at a certain negative voltage. At that voltage, what will happen, that we can say that it is a linear. So if we are drawing like this, so if these are the output characteristic of this, normal output characteristic will look like this, right? And if we are just extrapolating the results, they will all meet at a certain negative voltage, let's say as minus VA. So at this VA, it looks like that there is a linear connection between this VA towards the output currents. So let me now just write it down. So this is IC, that is the collector current or the output current. So we can kind of see that there is a linear connection between the early voltage towards the output current. So they have a linear starting point, and if we are extrapolating them towards the negative axis of the voltage applied, we can say that there is a certain amount of voltage from where it looks like they are starting from there itself. So this amount of voltage is called the early voltage, and because of this it is called an early effect. So they are starting very early. We are not seeing them in the device itself, but it looks like they're starting very early, from even from the 0 point. So that's why it's called the early effect or the early voltage. And as the base width is getting modulated, so based on that it is also called the base width modulation. So if you have any
Okay,
specific
sir.
question on this, oh okay, that's fine. So if you have any basic question on this, so you can also ask. So if there are no questions further, so we'll start with the problem. So today we'll have like a small number of problems as well. So the first problem is the parameters for the base region in an NPN BJT is Dn equals to 20 centimeters square per second, NB naught equals to 10 to the power 4 per cc, and ABE is 10 to the power minus 4 centimeters square. Okay, so ABE is the area of the base emitter, and Dn is the diffusion what do we say, like diffusion coefficient, and in B naught is uh, the carrier concentration of like in the region of B, that is the base region. Now they are saying that the base width is 1 microns. Determine the value of collector current when base to emitter voltage is 0.6 volts, and when collector base junction is reverse biased. In this case, you have to also assume that thermal voltage is 26 millivolt. So it is the most common constant we already know. So this value comes out to be 0.026, right? This is the most common constant here. So like remembering the formulas is very tough. So based on that, I am just giving the formula. So in a case in base collector junction, uh, base collector reverse biased junction, the value of the collector current, that is IC, is nothing but QABE, area, divided by XB, the depletion width, divided by NI square, by NAB dN, exponential of QVBE by KT minus 1. This is the basic formula. So you have to just put the values and get the result. So take a minute or two and give me the answer. So has anyone got the answer? All the values are given here already. So I'm just putting the values here. Let's start with Q, that is 1.6 into 10 to the power minus 19. EB, that is given as 10 to the power minus 4, divided by XB. XB is given as, where XB is given, XB, yeah, XB is given here. So 1 micron, 1 micron. So as we are like equating everything in centimeter, so this will be nothing but this. So anyways, these two terms will get cancelled out and multiplied by Ni square by Nab. Okay, so this term is nothing but minority carrier concentration in base region, right? Or which is nothing but Nb not. So we can say this is uh, sorry. So this is 10 to the power 4 per cc multiplied by Dn. Dn is 20 multiplied by e to the power of Vb. Vb is given as 0.6. So 0.6 into and 0.026 minus 1. So these are the just the values. Just put the values and get the answer. I'll also put the values. Just a second. Mm, 0.0156. So 0.0156. So this term comes out to be 1.6 multiplied by 20. You can turn on your mic if anyone has done this. You can turn on your mic and just tell me the answer, or you can also write down in the chat box as well. 10 to the power minus 15 multiplied by 1.0, sorry, 1.0157 minus of 1. So the final value would be minus 1. So it's like this, multiplied by 1.6 multiplied by 20 multiplied by 10 to the power minus 15. So let's just do this, right? Minus 15, 10 to the minus 15. Any other values? So 10 to the power of minus 15. These are, are there any mistakes? So it comes out to be like this. I don't think so.
Sir,
Ah,
the
yes.
base is one micro means 10 power minus 6 will come, sir.
What?
No, sir, no, one micrometer, no, sir. Base width. X.
Ah, yes. But uh, here, so this was in NB is in per cc, right? So this is centimeter per centimeter cube, and AB is also 10 to the minus 4 centimeter square. So this will cancel out, and it will comes out to be cm, right? So that's why I am converting it from micrometer to centimeter. So that way it will cancel out the centimeter. So like let me write it down. So here NB naught is in per cc, right? So that is centimeter minus 3, and the area is in centimeter square. So if we cancel them out, it will comes like it will come out to be cm, right? And to cancel cm out with cm, that's why I am converting this base with. So the
Okay, sir.
so I am using the base width limit as cm to cancel them out. Nothing but that. But there might be like a calculation mistake from my side. Let me do this. 6. Mm, so what I am getting is like I am getting this value. Someone also like try to do this. So I guess I am doing something wrong here because this won't be this high answer. So my answer is coming out to be 5 into 10 to the power minus 16. But I guess there's a mistake somewhere in putting the values or something. And this will be also in amperes, right?
So I'm getting as 5.024 into 10 power minus 16.
Yes, I was also getting I was getting 5.03114 into 10 to the power minus 16. So I was getting that, but I guess there's a mistake somewhere. So right now let's leave it. If we have some time remaining, like after the problems will come back to it. I guess there's somewhere I have done some mistakes or something. Oh, got it. Just a second. Yeah, so here this was a mistake, right? Yes, this is a mistake because to convert it, uh, just use a different ink, I guess. So here, this thing can be written as this, right? EVBE divided by VT. So divided by VT, not multiplied, because VT is nothing but KT by Q, not Q by KT. So here I am doing the wrong thing actually. So this value would be 0.6 divided by 0.026. So there was a mistake. That's why I was thinking why there is this higher amount. So this comes out to be 23.0769. And if we are minus 1, so what was it? 0.6 divided by 0.026. Exponential of this is, no, wait a second, 0.6 divided by 0.026 is this. Exponential of this, okay, sorry. So this is exponential of this. So that means this is nothing but 10 to the power of 10 because it's 0.05 into 10 to the power of 10. This is the value actually. So we have to multiply this value. So just like subtracting 1 from it is nothing. So that's why we'll just do this. So multiply it with 1.6 into 20, multiply it with 10 to the power of, sorry, multiply it with 10 to the power of minus 15. Okay, so now it looks like a good answer. So it comes out to be 0.000333676 amperes, or we can write it as like 0.33 milliamperes, right? 0.33 33.6. So let's write it as 0.34 milliamperes. Now it looks quite okay, but please like redo the calculations again. So there may be some like calculation mistakes as well, but it should come in the range of milliamperes in normal and physical cases. So it should be in the milliampere range to an ampere range, not like that much lower. 10 to the minus 15, you can't even measure that value. So that's why there was a mistake. I guess this would come nearly like this. So we'll move to the next problem then. Yeah, Q2. Now, in this case, consider that that the base transport factor in BJT is alpha t 1 by cos hyperbolic xb by lb, not lv, lb. Yes, where just remove it. So find out the base which um, base width needed in a PNP BJT to achieve a base transport factor of 0.9967. Okay, and they have also given that the diffusion coefficient is 10 to the power 10 centimeter square second, and minority carrier lifetime is 10 to the power minus 7 seconds. So like we know that alpha t has a value of 1 by cos hyperbolic xb by lb. Now xb is the base width which we have to find out actually. So we need to find out the base width needed in a PNP BJT to achieve a base transport factor of. So they have also given alpha V as 0.9967, and whereas LB is the minority carrier diffusion length in base. So base minority carrier diffusion length is LB, base width is XB, and we have alpha T of 0.9967. So we have to find it out, find out the value of XB, and we also have diffusion length that is DB, and also the minority carrier lifetime that is tau B. So it is a very simple formula. Take 2-3 minutes and try to solve this. So I'll provide the answer if nobody has got this. So just we have to nothing but do this, right? Cos hyperbolic xb by lb equals to alpha 1 by this. And so we can write it like this, right? xb is lb multiplied by cos hyperbolic inverse alpha b inverse. So this is the basic value of this. Oh, sorry, I forgot to turn on my mic. So this should look like this, right? And based on that, we also know that the value of LB, that is the diffusion length, is nothing but root over of dB tau b. So from this we can get the value of this equals to, from this we can get the value of this. So this is nothing but 10 multiplied by 10 to the power minus 7. So that is root over 10 to the power minus 6 or 10 to the power minus 3. And this was in centimeter per second. This one second. So this will be centimeter, right? Now the value of xb is 10 to the power minus 3 centimeter, and cos hyperbolic inverse alpha t was 0.9967 inverse. Just let me put it here. 0.1 by 1 divided by 0.9967 is, so this value is nothing but 1.00331. 1.00331. Now if we are doing this, so it should be, the value should be 1.00. So this comes out to be 10 to the power of minus 3 multiplied by 0.0814. So this is nothing but, or we can write it down as like this, right? So this is 10 to the power minus 3. So this was in centimeter and this was in centimeter. So if we want to write it down, so it will look like 0.814 micrometers. So this is like this, 0.814 microns. So the base width should be 0.814 microns. Now we'll move to the next one. Oh, sorry. Question number 3. Which of the following in the BJT is the heavily doped region? A is emitter, B is base, C is collector, and D all are equally doped. So any one of you can answer this.
The emitter.
Yeah. So in both the cases, in NPN and PNP, the emitter is the heavily doped one because it will emit either holes or it will emit either electrons, but it will be the heavily doped. And apart from that, these two are the moderately doped ones. Moderately. So don't get confused with PNP or NPN kind of a structure. So in the question, it can write also like in PNP transistor, PNP BJTs or NPN BJTs. In both the cases, the emitter will be the only heavily doped case. So we'll move to the next one. So we'll have another this kind of a thing. So which of the following is true? Let me write here. One, the base width must be larger than the minority carrier diffusion length. The base width must be smaller than the minority carrier diffusion length. Her the base region should be heavily doped. And fourth is the base width must be much smaller than the minority carrier diffusion length. So tell me which one is true and why. Sorry for the bad handwriting. I was writing fast, so I didn't.
Sir, the fourth one,
Yeah, fourth one and why. So that is correct. The third
because
one is obviously wrong because it, as we have already discussed in the previous one. So why the first one and the second one is wrong?
because as compared to emitter and collector, the width of base region is very less.
Yeah. So like in this case as well, right? This is smaller and this is much smaller. So why the need of this much smaller?
So as being a moderately doped.
So being moderately doped, how does it like changes the much smallerness of the base with? So we know the formula is this, right? WB should be much less than LB. So it's perfectly correct answer. But why? So we know that this diffusion length is the average distance traveled by the minority carriers before recombination. So why does we need to take this much smaller? Why not smaller? So this one is wrong, obviously. So this is also right.
Sir,
Otherwise, there will be recombination.
if the width of base region is less, so the number of so maximum charge carrier are easily transferred from emitter to collector.
Yes.
That's why the equation like IE is equal to IC plus IB. So I think uh,
No. So what is our main aim? Our main aim is to reduce the recombination, right? Now the problem is that just a second. Yeah, so we have to just reduce the recombination. Now the problem with recombination is that the diffusion length defines the average average distance traveled by the minority carriers before recombination. Now, if we are taking this as like this, what will happen? As that is the average length, so many of the minority carriers may may recombine before even reaching the opposite side. That is before reaching the collector site. So it will recombine within the base itself. So there will be a very less current in that case. So that's why we need it to be much lesser to reduce the amount of recombination happening. Because the basic problem with the definition of LB is that it states the average distance traveled. So average distance that can be traveled by a minority carrier before the recombination happens. So we need it to be maximize this. So the WB should be much lesser than LB. Otherwise, in this case, so like if we are stating this, let's write it down. So in this case, there may be a higher amount of recombination with respect to WB less LB. So why we are saying maybe? Because it's the average length. So we don't know for an exact minority carrier will it recombine before that average length or after that average length or something. We don't know exactly. So we are saying there may be a higher amount of recombination happening if its WB is less than LB. So just omitting the fact that we don't any kind of a recombination in the base region. So as we already have learned from this, like from the non-idealities, that there is a very small amount of recombination happening, so we need to reduce it as much as possible. So that's why we are moving towards WB less LB. So there's a follow-up question on this. So why do you think we can't completely reduce the recombination? So if we are making it WB much lesser than LB, we can make it much lesser than that, right? So if it is already not comparable to the value of LB, we can make it much smaller than that. So why are not we making that? So we can also avoid the that non-ideality case as well. Why are we not making that? What do you think? One of you can answer this.
Sir, due to channel length modulation.
So what will happen? The answer is partially correct, I would say, but so due to there's also another non-ideality called the punch through. So if it's much lesser than that, and if it's is tending towards zero, then there will be another problem called the punch through effect. So we need to avoid that as well, and also we need to take in consideration that it should be much lesser than LB as well. So there is also a lower limit in this case, and we have also a higher limit in this case as well. So we can't make WB like as much lower as possible. Also from the fabrication perspective as well, like we have a limitation, right? We can make it a very smaller something. So there's a fabrication limitation as well, and the basic limitation is the punch through effect. So we'll move to the next one, question number 5. So in a BJT biased in the active mode. So as already told, what is the active mode? Active mode is the also known as the analog mode, where the transistor is behaving linearly, right? Now, as they have said, the base current, sorry, the base current is 6 milliamperes, and the collector current is 510 510 microamperes. Find alpha. So it's a very simple one. Take a minute or two and try to solve this. And like also consider that it is in the linear region, so it is in the active region.
So 0.98.
Yeah, that's the correct answer. So for the others, I'll just do this. So beta is nothing but the ratio between collector current and the base current. So that is nothing but this divided by this. So we can write it as 85. And also alpha is beta by 1 plus beta, and we'll do this 85 by 86, and this comes out to be 0.988. So that's the correct answer. Now we'll move to the next one, question number 6. And so sorry, just a second. Consider a uniformly doped NPN BJT in forward active mode. We get VCB is 3 volts. Collected to base voltage is given as 3 volts. Okay. Now they have given the base width is 1.1 microns, emitter base and collector doping concentrations are 10 to the power 17 per cc, 10 to the power 16 per cc, and 10 to the power 15 per cc. Determine the base emitter voltage such that minority carrier concentration at x equals to 0 is 10% of the majority carrier, that is the whole concentration. And anyways, it's given. So try take two. I don't think it will be done in two. So let's take 3-4 minutes and try to solve this. So like I'll just go through the problem as well. So they have given the value of VCB, that is 3 volts. they have given the doping concentration of emitter is 10 to the power 17 per cc. Doping concentration of B is 10 to the power 16 per cc. And sorry, doping concentration of collector is 10 to the power 15 per cc. And they have given, what have they given? The base width. So they have also given the base width as how much? The base width was given as, yeah, so base width is given as 1.1 microns, and also we need to calculate the value of VBE, base emitter voltage, and they have given that minority carrier concentration at x equals to 0 is 10% of the majority carrier. So try to solve this. We have to just get this. Are there any other things? I don't think so. Yeah. So try to solve this. Has anyone got any kind of a clue how to solve this? So maybe I'll start with a basic thing. So first we need to know what is NP naught, right? So the value is nothing but Ni squared by NB. So in the B region we are calculating this. So we are just having this value 10 to the power 16. So if we are putting the value, it should come out like this per cc. Okay. Now at x equals to 0, we need to find this value x0 equals to np naught e to the power of vbe by vt. Okay. From this we can also write that vbe is nothing but vt into ln of, now we know the value of vt anyways, so ln of np x equals to 0 and np naught. Now in the side we can also do this. So what is the value of uh, what is the value of np at x equals to 0? So it was given as 10% of the majority, sorry, this is 10% of, okay, so this is nothing but 10% of NB, or 10 by 100 of NB, or NB by 10, nothing but this. So we know the value is 10 to the power 16 by 10. So this is 10 to the power 15. Now if we put this here, the value is 0.026. We know this value. ln of this value is also known 10 to the power 15, and we have got this 2.25 10 to the power 4. So if we put the value, let me just put the values here. So 10 to the power of 15 whole divided by 2.25 divided by 10 to the power of 4. So this is 4.444 into 10 to the power 10. We have to just log it. That is 24.5. So this is 0.026 multiplied by 24.5175. Let's write it like this. Multiplied by 0.026. This. So the value is 0.67 63745 volts. Now, so in this calculation, there were other like cases as well. So if we considered, so now as we know, so we have considered this value, right? So in this case, we also could have considered as 10 to the power 10. So in that case, the values would have been um 10 to the power 10, that is 10 to the power 20, 10 to the power 4. So the values would have been 10 to the power 15 divided by 10 to the power 4, that is nothing but 10 to the power 11. So ln of that value should have been 25 point something multiplied by 0.026. So if you are doing this using the value 10 to the power 10, it would have come out as 0.6585 something volts. So both of the answers are correct, as there is no like given value of this, so you can put it like 1.5 into 10 to the power 10, the ni value, or 10 to the power 10 as well. So but both are in per cc obviously. So it can be 1.5 into 10 to the power 10, it can be 1.0432 into 10 to the power 10, or 10 to the power 10. So every value is correct. So it would have like you would have gotten a range of this value. So this is 0.635 63745, or 0.658, something like this. And so this value was not in use, this value was not in use, this value was not in use as well, I guess. Yeah, so this is it. And we didn't also needed this value as well. So everything was like there to kind of confuse you or something. Okay. So if anyone have any questions, you can ask me. Otherwise, we'll end the session here. Oh, sorry. Someone have no for the last question. That's fine. So if anyone have any question, please ask me. Otherwise, we'll end the session here. And from the next week onwards, so we'll start the MOS caps and MOSFETs. That is the metal oxide semiconductor capacitors, because we need to know the COX values. That is the oxide capacitance values and the capacitance density and those things what we have already learned and will implement to the MOS transistors. And in those MOS transistors, we'll learn more about these current and voltage characteristics and how the band bending is getting affected and these kind of structures. So in this class, what we have learned will also implement those things in the MOS transistors as well. Few of the things will have a different kind of term. So like here, it is called the base width modulation. This will be the channel width modulation, and based on the width and length of the channel, the everything would be dependent and everything. So we'll learn that in the next class. So I guess we'll end the session here if anyone have no questions. So thank you for attending today's session. Thank you.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you.